Okay students, I hope you are all well and healthy and ready to learn new things. So my name is Palak Patel. I am working in the Mahatma Gandhi Institute of Technical Education and Research Center Navsari in Civil Engineering Department. I am going to teach you the subject is design of structure. So in this subject we are going to learn continuous beam design. So be ready and good luck.
So students, we found a load. Okay. So we have this graph. Okay. Okay. This drawing. In this drawing, we got a live load, total load on the beam, and right now we are going to find I. For the I, we are assuming the beam dimension as well as column dimension. These are the assumed beam dimension as well as column dimension. So size of beam is 230 by 300. These are assumed. So by this assumption we have to find out I equation is BD cube by 12. So 230 into 300 by cube divided by 12. So 517.5 into 10 raised to 6 mm raised to 4. Same thing for the column. We assume a column size is 300 by 300. So I is 675 into 10 raised to 6 mm. Then after we have to find out fixed end moment. So for the fixed end moment, MFAB WL square by 12. Okay, so W is 50.75 into 10 raised to 6 whole square into 6 whole square divided by 12. So what is W? W means total load on beam. Okay, MFAB. You can see, so in the figure we have the beam which names AB, and after BC, then after CD. So for the fixed end moment on AB is WL square by 12. W means total load, L means length. Okay, L means length. So for the WL square by 12 we got a fixed end moment minus 152.25 kilonewton into meter. Then after MFBA, fixed end moment at BA member, equation same, WL square by 12 plus 152.25. So how this happened? You can see here it's A and B. Our moment it this direction. Okay, so A here, B here, it's anti-clockwise, so minus is clockwise means plus. Okay, same equation for the MFBC, WL square by 12 minus 62.42 kilonewton into meter. Okay, then after MFCB plus 62.42, MFCD minus 152.25, MFDC plus 152.25 kilonewton into meter. Sorry. Then after distribution factor, we have to find out distribution factor. So for the distribution factor we have a table, serial number, joint, member, K upon IL, K df K upon sigma K. So joint A have a three member AE, AB and AI. Okay. So I is column, A is a column, is A joint E and I. E is a column, E is a column. Okay. For the column we have IC is 675 into 10 raised to 6. 675 into 10 raised to 6. Divide by length. Length is height. Height between the floor, which is 3350. So by this equation we can find out K. It's I by L. So I by L we can find out K. K means stiffness. So value is 2.01 into 10 raised to 6. Same equation for the AB. AB is a beam. So I is 517.5 into 10 raised to 6 divided by 6000. So value is K is 0.86 into 10 raised to 5. Okay. AE value is 675 into 10 raised to 6 divided by 3350. So value is 210 into 10 raised to 5, 201 into 10 raised to 5. Sigma K means summation of all three members. Summation of all three members stiffness. 2101 plus 0.86 plus 2.01. So sigma K is 4.88 into 10 raised to 5. 4.88 into 10 raised to 5. So distribution factor is K divided by sigma K. For the AE, K is 2.01 into 10 raised to 6 and sigma K is 4.88 into 10 raised to 5. Sorry. Okay. 10 raised to 5. So K is 0.412. Okay. Same formula for AB, AE, joint D, joint C and joint D. You can try by your own self. Okay. Try to find out distribution factor for the C and D by your own self, yourself. So find out distribution factor, we have to distribute a moment. For the distribute moment we have a joint members, column A, B, BA, column B, column C and column D. So we write down the distribution factor here, which we find out in the above table, and these are the fixed end moment. This is the fixed end moment, and then after we have to balance, coordinate, balance, coordinate, balance, coordinate, balance, and then after final moment. I hope you know how to distribute a moment distribution method. Okay, then after we got a final moment here, 132.05, 132.1, 150.22, 75.37, 74.59, same as the all members. These are the final moment. So by the using a final moment we can design a beam. Okay, first of all we have to find out column moment. So here is a column, you can see MAE and MAL. We got two moment here, 132.05 divided by 2, so 66 kilonewton into meter. This moment is applied on the both column. Okay. Same for MBF, MBI, MCG, MCK, MDH, MDL. So by this all the method you can find out column moment. So these moment are distributed in the column. Okay. Then after shear correction, we have to find out shear correction. Shear correction V plus free shear plus or minus net moment about span. Okay. So for the VAB, 15.75 into 6 divided by 2, it's a free shear, means a shear force, means a reaction. You can see here is a beam A and B. Load on the beam is 15.75 6 meters span. UDL load, this reaction at A and the reaction at B, this equation is WL by 2. So this equation is here, 50.75 into 10 raised to 6 divided by 2 minus 150.22 minus 132.05 divided by 6 minus 150.22 minus 132 divided by 6. So reaction is 149.22. 150.22 is fixed end moment, and 132, this is a moment which is balanced. Look at here, 150.22. Okay, so these are the moment here. So by the moment we found out shear force, shear correction 149.22. Same for the VBA, VBC, then after VCB, VCD, then VDC. Okay, so these are the shear correction. Now we have to find out maximum moment on the beam. So we are going to design a continuous beam. Okay, in a G plus rebuilding, we have a moment fixed end, but we have to design a maximum moment here. We need a, so here we need a maximum moment for the design. So we found a moment here, shear force here, and load is here, but we have to design a beam for the maximum moment. Okay, and where the moment is maximum? When shear force is 0. So we have to find out where our shear force is 0 on the beam, and then we will find out maximum moment. First, for the span AB and CD, so maximum bending moment occurs when shear force is 0. So we assume shear force is 0 from distance x from A. Okay, so shear force is 149.22, it's a reaction at point A. 50.75, it's a load, into x. When this both value is 0, our shear force will be 0. So we can find out x, 2.94 mm, 2.94 meter. So by this meter we can find out maximum moment. At 2.94 meter we have a maximum moment. So maximum moment is 149.22. It's a reaction at point A into 2.94 minus 50.75. It's a load, and 2.94 whole square divided by 2 minus 132.04. It's a fixed end moment. So by this equation we can find out maximum moment is 87.32 kilonewton into meter. These are the maximum moment on the span AB or CD. Then after we have to find out maximum moment on span BC. On span BC we have to fix end moment, shear reaction, load, and shear force is 0. Let shear force is 0 at a distance x from B. So here is shear force is 93.64 is equal to 46.82. So x is 2 meter. Okay. So by this equation, same equation, we can find out maximum moment is 90 19.05 kilonewton into meter. Okay. Now here we have a maximum negative moment at support. This is the fixed end moment or a final moment we will find out from the moment distribution method. Now we are going to design beam AB and CD. So maximum moment at a mid span is 87.32 kilonewton into meter. We assume width of beam 230 mm, depth 450 mm. So effective depth is 400 mm. 50 mm cover is minus. Okay. Then we have find out mu limit 0.138 FCK BD square 0.138 into 20 into 230 into 400 whole square. So by this equation we can find out moment limit 101.56 kilonewton into meter. This is the moment limit. Okay. Here is moment 87.32 and moment limit is 101.56. So these are the lesser moment. Okay. Mu less than mu limit 87.32 kilonewton into meter less than 101.56 kilonewton into meter. So on the beam we have a maximum moment 87.32 but moment limitation is 101.56. So we can design here a single beam design. Okay. For the single beam design, mu upon BD square 87.32 into 10 raised to 6 divided by 230 into 400 whole square into 2.87. PT is 0.785 percentage. From the SP60 we can find out PT percentage of steel at a tension zone. PT we can find out AST 0.8 PT BD by 100. So AST is 722.2 mm. Provided 60 mm diameter at 4 numbers of bar at a mid span. Same for the BC. Mu is here. We can find out mu BD square 0.152 and PT is 0.149. But we have a limitation here. We cannot provide less than 0.2 percentage of steel. We cannot provide this. So PT is 0.149. So provide Fe. So 0.2 percentage we have to provide PT. Okay. So by the PT 0.2 percentage AST is 0.2 divided by 100 into 230 into 400. So AST is 187.68 mm square. Okay. Then after provide 2 numbers of diameter bar at 60 mm diameter at bottom. So we design our reinforcement at the center. Now we have to design at the support. At a support A and D. At a support B and C. So moment is here minus 132.05 minus 150.22. Mu less than mu limit. So at the support we have to design a WRC beam because here we have a 150.22 kilonewton into meter moment. So mu2 is equal to mu minus mu limit. So mu2 is 48.62. Assume top effective cover is 300 mm. D by ds 300 by 400. From the SP60 we found FSC, FCC. We found FSC and FCC. So right now we can find out AST, mu minus mu limit, FSC minus FCC. So ASC is 382.22 mm square. Put the all values here. Put the all value in the equation. Mu minus mu limit is equal to FSC minus FCC into ASC into D minus D dash. So mu minus mu limit is mu2, FSC, FCC we find out here, ASC we have to find out this, and D minus D dash, D dash means effective depth and D dash is effective curve from the top. So ASC is 382.22. Now we have to find out AST1 for M20. PT is 0.96 from the SP60 table A page number 10. From the PT we can find out AST 3.20 mm square. To find out AST2, we have equation FSC minus FCC into ASC divided by 0.87 Fy. So here is the equation AST2 364.25 mm square. Total AST1 plus AST2. So total AST is 1247.45 mm square. Provide 4 numbers of bar as 20 mm diameter at the support P and C. Extend this bar to L by 4 either side from the